All right, good afternoon, everyone. Welcome to the next of the QBEST Energy webinar series. I'd like to welcome Alan Day, our special guest. Hi, Alan.
Hi there, Andrew.
And Jonathan Mendez, also from the QFF team. Hi, Jonathan.
Hi, Andrew.
And I'm Andrew Chamberlain from the QFF Energy team. So today's webinar, it's a big title: Aquaculture, Voltage, Power Factor and VSDs, a case study of a North Queensland Barramundi Farm energy audit. And it's actually a blended case study of a couple of North Queensland Barramundi farms, but also incorporating some experience of Alan's on previous large farm audits and aquaculture audits as well. So I'll just give a quick intro. We've turned off mics and cameras for participants, but please feel free to jot down any questions that you might have as the webinar goes in the chat or the Q&A boxes at the top, and we'll get those questions to Alan and we'll answer them before the webinar. We are recording today, so we'll put this webinar up on the Queensland Ag Energy Hub website afterwards. And yeah, just again, please remember to add any questions or comments you might have to those chat icons at the top of the screen there. I'll just do a very quick introduction. We'll cut to the presentation from Alan, and then we'll have some time for questions and answers at the ends, and then we'll go to just give a quick wrap up with some next steps and things you can do from here. QBEST, so Queensland Business Energy Savers Transformation Program. It's a program that we're running here at Queensland Farmers Federation for the Queensland Government. We're doing 35 Type 2 and 3 energy audits on farms throughout Queensland of different sectors and different farm types. And Alan has done a couple of those for us on some farms in North Queensland. We're doing Type 2 and Type 3 energy audits, which are very detailed energy audits, with Type 2 being a whole of farm assessment, and Type 3 energy audits being quite specific system or subsystem audits. And you can find out more about those at the Queensland Ag Energy Hub, which we've also developed as part of this program. So it's a one-stop shop for energy information in Queensland. In particular, we've got over 100, probably 120 energy efficiency case studies from all the various energy programs that we've delivered at QFF here over the years. I'd just like to introduce Alan, our presenter. He's from Tailored Energy Solutions based in North Queensland. I met Alan probably 8 or 9 years ago. Alan doing some energy efficiency workshops for farms back in North Queensland when we were doing some programs with Ergon. So you've been doing this for a long time, and like I said, you've delivered a couple of energy audits for us on a couple of large farms as part of this QBEST program. So there's Alan's contact details there. So please feel free to get in contact with Alan directly after the webinar if you like. But Alan, great to have you on board. Thanks for joining us today, and I'll cut to you for your presentation.
Thanks, Andrew. Thank you. So we'll just bring that up. Is that all good?
Yes.
Okay.
Perfect.
So we were asked to have a look at a couple of barramundi farms up in far north Queensland. So these are in the Mossman area, and the one that the focus of this particular presentation is Saltwater Barra Farm at Wonga Beach, which is just north of Mossman. The other one was also a very good operation that's up on the tableland, and that's a freshwater barra farm. But you know, for people that have seen barra farms before, this picture just shows you it looks more like a botanical gardens than a barra farm. They don't, in our experience, they don't usually look like this, but it's a very impressive operation, very well run. I'll say right now, when we would have gone there just about 6 months after they'd had a major flood with the major rain event that happened just after Cyclone Jasper in December. So it was quite devastating for them. They basically, the ponds flooded, they lost huge amounts of stock, plus damage to equipment. And I think the damage bill was in excess of $1 million. So, you know, it was pretty painful. But having gone there in August, you wouldn't see any of that. They've done a fantastic job to bring it back. But they are still in recovery mode in that while they've got the place looking good and the equipment's working well, they're still basically in the process of restocking the whole farm. So they lost pretty much all of their stock. Just something that, you know, we really felt for these guys. They're a great operation, as I said. So moving on to the level 1 and level 2 audit and looking at their energy use and power bills, we took their annual numbers, but then we adjusted them for the impact that Cyclone Jasper had, so that it gave us a more normal set of operating costs. So you can see from that slide there, annual bills $170,000. And it's split down basically per the pie chart, with 107,000 as energy, 47,000 for excess demand charges. So they're on T44, so they get charged for everything over 35 kVA, and they're in a pretty cruel place from that point of view. And then the fixed service charge of $16,000 based on T44's round about $45 a day connection fee. So when you look at the detail of the table on the left, you can see that their kVA is generally around the 158 kVA mark. So as I said, everything above 35 kVA is considered to be excess demand. So they're in a pretty bad place, but at the same time, that high cost of 47,000 is a great target for us to target, to look at to help reduce their costs. This is from the interval data that we received from Ergon Energy. I've just focused on, that's the daily load profile. So it's the average load profile for 365 days. So it's quite a good indicator. The real surprise is that peak that happens at about 7:30 every morning. I suppose more of a surprise is nobody knows what causes it. And when we looked at the farm, because it has a tourist facility with a cafe and a hookahbarra facility, which is always busy, we assumed that might be when they're turning on appliances in the kitchen and all those kind of things, but we're told that's not when that happens. That's too early. So at this point in time, we've not been able to identify what that peak is, but it's clearly would be a great target. If we understand what it is, we might be able to level that out and shave that peak off a bit and get them a result there. But it would require more work to find out what's happening in that space. So just again, and Andrew sort of covered this is the level 2 audit process, which is the desktop review plus a site visit to understand the farm and identify the equipment and try and start spotting what kind of cost-saving opportunities there might be. And then in this instance, we move straight on to going into detail on some of those improvement processes. So just in terms of the tariff review, you know, they're on T44. Basically, Ergon, with the removal of agricultural tariffs, have limited their options. There are no time of use tariffs that make any kind of sense for this farm. It's 24/7, so you know the load's pretty level through the period. So there's nothing you can really achieve looking at time of use. But we do believe it's worthwhile for the farm to consider an alternative retailer, and we'll talk about that a little bit later. But but we've seen a number of our customers do this, and they can generally save about 10% of the cost of their energy. But people really need to understand what they're doing if they make this change, because it isn't straightforward. And again, we'll talk about this a little bit more a little bit later. It's also possible these days to use a number of different methods to access the NEM wholesale market, which can work really well if you've got a business with a high daytime energy use, because in the wholesale market, prices are often going negative through the middle of the day as they're oversupplied with solar feed-in. So that's good if you have a large daytime usage, as I said, but not if you've got a large nighttime usage when prices actually go quite the other way. So that the NEM wholesale prices basically don't really marry up in any way to the standard tariff prices that are being applied through standard ergon tariffs. Just to mention it, it will work for other businesses potentially. So, when we look at the farm, we think, is there anything they could be doing differently that would give them some savings? Maybe the way they switch machinery on, the way that the machinery is configured. But as I said, this farm is very well run. Everything is planned. Everything's well maintained. There's a very good maintenance schedule. Paddle wheels are pulled out regularly and fully refitted and then put back in. So, as I said, from our point of view, the only thing that we can see that might be an area that could provide a benefit could possibly be that peak that we have not yet identified that happens first thing in the morning. So just talking about the site, and obviously to do our job, we need to understand how the farm is set up and what their systems are. So what we have here is the farm water system, and it is well designed. Basically, you can see there's a creek that runs just to the right of the title farm water system. There's a channel that runs all the way up to the Daintree River, and that's a tidal creek. And they actually do get a very good water delivery down where they have their sea intake pumps, two 22 kilowatt Tsunami pumps, which are low head, high volume. And they feed into a ring main, which is just a great way to do this. And I know the pipes are a good diameter. They really don't have any problems with friction losses and those things. They'll either run one or two pumps, depending on how many ponds they're planning to recharge or refill. And so basically the water goes into the ring main. They open the valves in the ponds that they want to supply water to. And then the ponds are drained. That's the green arrows show the ponds draining to those channels, which ultimately are either pumped or free flow into the settlement ponds. And I don't show in this because it's that there are more settlement ponds further north. So basically they go through the settlement ponds where they have to then achieve certain environmental standards before they discharge back into the river. So they have a station where they test the water quality for oxygenation and various other things that I'm not familiar with. But the system's working very well. As I said, it's a well-designed system. The other thing I'd point out here, again, at the top of the page, you'll see sediment pumps 3. They're significant to us because that's the furthest most electrical load from the main switchboard. So we need to be aware of what's happening to voltage and supply at that point. And I would say prior to Cyclone Jasper, when they had this real setback, they do have approval to convert settlement pond 1 into more fish ponds, and they were well advanced in planning to do that, but they have to recover from the cyclone issues first. Incidentally, they do have plenty of water capacity for additional ponds. And we'll move on to the electrical network. They also have plenty of electrical capacity. So you'll see the main highway goes up on the left. That's the main highway up to the Cape, which is why I think their tourist facility always seems busy. They've got a cafe and as I said, Pond 8 has fishing platforms around it, so it's a catch and release. But yeah, while we were there, the days that we were there, it always seemed to have plenty of people going through there. So it's a great side business. So they've got a 600 kVA transformer. That's bigger than they need at the moment. The MSB shed, nice and close. All the electrical boards are in great shape, well maintained, well designed. And we know, and I'll show you in a moment, but we know from the voltage drops across the site that the cable sizing, and this is always very important, but the cable sizing is good. So their electrical network is well designed also. So you can see on there, basically, I have marked all the major loads. So that's from the two 22 kilowatt Tsunami sea pumps. There's four sediment pumps. They vary between 5 kVA and 7.5 kVA. An ice machine. So there's not a vast number of large loads. It's easy to overlook the actual paddle wheels, which are only 1.5 kilowatts, but there's 28 of them. So if you put those together, they form one of the largest loads on the site. And we actually think there's a plan that we have to address that also. So we'll come to that later. So these are the full detail of the loads where we have measured voltages. We've measured the inrush currents as all this equipment is started. And then we've measured the full load current when they're on steady running. So we've been able to identify the actual power factor versus nameplate. And we know what the starting kVA and the running kVA is. And this is the detail that starts to tell us where to focus when we're looking for ways to find savings. So I would just point out that the voltages are quite important. And again, I'll speak about that later, but you can see that from the MSB at 428 volts to the sediment pumps 3, that's your largest voltage drop, 23 volts, which is a little higher than you might like, but it's still well within the bounds of saying that there is no problem with the electrical cable that's been used to run power out to those pumps. The other thing, just to clear up, that a lot of people think that with peak demand billing, what happens is that Ergon manages to spot the very highest demand you ever put on your system during the month period, and you get billed at that rate. It's actually not quite as cruel as that. There is an averaging process. So peak demand charges are not simply based on the highest single recorded peak demand. The impact is a little less severe because it is averaged over every 15-minute period. So I just thought I'd mention that because I think, there is, it's not something that's very well understood. Okay, so these are the areas that we believe that we, decided we would be looking at to find ways to make savings. Just starting with something that's basically a no-cost administrative thing, if you like, and this is the alternative energy retailer. We've put all the other issues, not in order of payback, that comes later, but basically just working from the main switchboard out to the electrical equipment. It sort of takes it in a logical way through the whole plant. I think, I don't know whether I say it now, but one of the things that people really need to understand with this kind of approach of looking at improving the efficiency of individual pieces of equipment and the main switchboard and all those kind of things, is you really can only do those projects one at a time, because everything you do in those areas will impact everything else. So you really got to make the change, do a project, and then reassess the baseline, because the requirements, the sizing of VSDs, for instance, or the sizing of power factor correction equipment will change once you've done some of these projects. So it's a moving target, and it really should be really done one at a time. So moving on to the detail of the projects, and that, by the way, is the visitor centre. And you can see it's busy, a nice cafe, and it's got a special area with barramundi tanks, so people can have a look at them, and there's a life cycle of barramundi and all that good stuff. And yeah, it's pretty popular without doubt. So as I said, a great addition. And they're part of a group of businesses in that Port Douglas and Daintree area that group together different visits, so they'll get busloads of people turn up that are then going from there onto a croc farm, or some of the limoncello and limecello and all that, the people that make the booze up there. That's they're really kind of fitting into their local area. So we've seen that already, that this is the things we're going to look at. And first of all, the alternative retailer. So we've seen that businesses can get a pretty significant, very worthwhile cost saving by talking to an alternative energy retailer. But it's something that people need to understand before they jump in. And one of the first points to make is that an alternative energy retailer really does only contract to supply the energy. So what that means is that when you see your bill after you've made this change, you'll suddenly realize Ergon is still a very big part of it. And what happens is Ergon Network passes their charges through to the alternative retailer, who passes them on at cost. And you'll see that Ergon Network charges will be anywhere between 40 to 60% of the bill. So it's like, I say, it's like the Hotel California. You can leave Ergon, but you can never check out. So those charges will still include network charges, supply charges. They pass on the charges that they collect on behalf of the government to support all the renewable energy schemes. And that's a remarkable amount of money that's charged there. They charge you various costs to do with AEMO, marketing charges and admin charges for AEMO. So when you get an Ergon bill, you don't see that breakdown. You don't see that breakdown until you've made the change to an alternative retailer. And this is where there is more of a risk moving from Ergon for the first time to an alternative retailer, because the alternative retailer will tell you what they will charge you for your energy, but they're not very good at saying, by the way, you will still have all these other charges. So it's quite hard for you to see what the net benefit is. The other thing that people get nervous about, because I think people do know that if you move from Ergon retail, you can't go back. And that worries. I've talked to people that then say, well, so when we have a problem with our network, with our supply, Ergon's not going to want to know us. Well, I can tell you that really isn't true. Apart from anything, Ergon Network and Ergon Retail don't seem to like each other in the first place. So Ergon Network's not in the business of taking revenge because you've moved to a different retailer than Ergon themselves. So I have my view with this is that the best way to approach it is to find yourself an energy broker the first time you make the change. And, there are good brokers, there are ordinary brokers, and the best way to find a broker is get recommendations, ask them for references. They have to make a living. They do it in different ways. Some take a trailing commission on your new contract, and some will charge a fixed fee to do it. But I guess I would point out that once you've made that move from ergon, any renegotiation with another alternative retailer later on, or more of them, is actually very easy to do at that point, because you know what the ergon network charges are and they won't change. So it's much easier at that point to compare the offers from different alternative energy retailers. But I would recommend using a broker in the early stages, but be selective. Now, voltage optimization. So we're going to go through some slightly more technical issues, and I'm trying to keep it as simplistic as I can, or simple as I can, because it can become confusing. So I hope I do get this across as clearly as possible. The first thing to understand is ergon network, and in fact every network in Australia, is required to provide a low voltage grid, three-phase, we'll talk three-phase, of 400 volts within a range of 380 to 440. And that's -5% plus 10% on that 400. There's a smaller allowance below 400 because low voltage is more dangerous and more risky for equipment than high voltage. And so because voltage will always vary during the day and night, ergon tends to prefer to operate their grid at the top end of the range. It's less risky for them. If it drops below the lower end of their permitted level and there's damage, and you can prove that it's below the bottom of that level, then you can actually ask them to come and replace your equipment, repair your equipment, whatever, compensate you for the damage. So voltages at this farm varied from 428 at the MSB, as I've shown you, and the most distant voltage with the drop to the most distant sediment pumps is 405 volts. That's actually a little bit lower than we often see. Sometimes we even see it over the 440, to be honest, but this is actually not too bad. But the bottom line is that electrical equipment has what we call a voltage sweet spot. So if you're operating it at a higher level, that excess power is generally just dissipated as heat. It's wasted. And more than that, Australia follows the National Electrical Manufacturers Association standard for motor design, and they have done that since 2002. And what that means is that all motors are designed to be most efficient at 380 volts. And as I've just said, actual supply voltages are higher, usually higher. So if you look at this chart, you'll see that at 380 volts, it's the sweet spot for close to the minimum amperage. It's the convergence of efficiency and power factor. And if you move off to the right to where I've just shown 418 volts, for instance, you can see that the motor will draw more current, the efficiency falls away a bit, and the power factor reduces a lot. So voltage optimization is really about moving the voltage, the operating voltage for the pumps towards that optimum. So let's have a look. This is just showing how the supply voltage is modified by voltage optimizer. But it's probably easier just to explain. This is a voltage optimizer. So you can see the whole unit onto the right in the middle there. That's what it looks like. So just a big electrical board. The readout is just an expansion of the readout that's on the front of the machine there. And on the left, you see that this is basically an auto transformer. So it will take whatever voltage is thrown at it, and that can be a lower voltage than you want, as well as a higher voltage. So it will constantly adjust to give you the voltage that you program in. So if you look at that if you can make out the numbers on that panel, you can see the incoming voltages to this particular site. This is in single phase, obviously, phase to earth, 250 amps, 251 amps, 252 amps. So the three phases are slightly out of balance. If you look at the panel below that, you can see that they've set this voltage optimizer at 221 amps, and it's absolutely even across the phases. So basically, voltage optimization works very well with inductive loads, which is what we guys are always talking about, pumps and refrigeration and those things. As I've said already, if you have other energy saving devices such as VSDs in the system, it will impact on the result here. And that's why, as I said, you've got to go back to the baseline. Every time you make a change, go back and measure again. Voltage optimization will not do anything for equipment that has inverters, LED lighting, or DC equipment. But another quite good benefit from voltage optimization is that, as I said, it corrects for whether you've got an overvoltage situation or an undervoltage situation. So it protects you against surges and brownouts, which can extend the life of motors. This is just an example that we were provided by Captech, who are the guys that we've used with voltage optimization before. So this is a supermarket in Victoria. It's quite an interesting slide because you can see that variation in the top set of colors. Lines are basically what's being supplied to the supermarket. And you can see, firstly, there's quite a bit of variation between the phases, and they're quite erratic. And what you're seeing here, those peaks, you see the three peaks in the curves. This is showing you a phenomena where I would say there's quite a lot of solar capacity around this supermarket. So those peaks happen when, during the middle of the day, when you've got lots and lots of solar systems trying to pump energy into the grid, and that increases the voltage. And these are the issues that Ergon and the other providers have to deal with. So Ergon would be particularly pleased with people that make this kind of change because it stabilizes the grid for them to a large extent. So you can see this particular optimizer set to a voltage of 222 volts. And you can see how stable that's been throughout this period, even though the supplied voltage has been quite erratic. It's also reduced the variation between the phases. So it's reduced the imbalance between the phases. So I think that demonstrates how effective this equipment can be. So cutting to the chase, if you like, I won't go into the sizing of the unit for the Daintree farm, but basically if you install 160 kVA optimizer at the MSB, and this is a unit that has to sit between the transformer, the Ergon transformer, which is a 600 kVA at the side of the property, and the MSB. So it's in series. So it's a serious shutdown job to install it, but otherwise not that complicated. So even if you set that at 400 volts and manage a 12% saving, you can see that the payback's 5.2 years, which, you know, people tune into, I find, the payback period quite well. So that's actually quite a reasonable kind of outcome. The other thing I should say, by the way, all the costs that we use for equipment and installations through this project are intended to be pretty conservative. So the real outcome could probably be better than that. But we have not included this in their plan because we know of their financial situation, and there are other projects which will give them much better paybacks that we think they should prioritize. And one more thing, This is the poor man's voltage optimization. Basically, talk to Ergon. You know, these guys have their own dedicated transformer, and you can ask Ergon to retap that yourself. And they're sometimes reluctant to do it, but where you have a dedicated transformer and you've asked them to do it, there's no real reason why they should say no. So you can achieve part of the benefit just by doing that. Obviously, it's not protecting you from power surges and brownouts and those kind of things, but it's a pretty good halfway measure to getting a cost saving up front. Okay. My favorite picture. It's time for a break. So power factor correction. I'm really not fond of this image, an explanation of power factor, and it's one that's used to explain it to electrical apprentices and all sorts of people. And the idea is that you can only drink the real beer and the fluff on the top is just a waste of time. So the thing I don't like about it is that the implication is that reactive power is a waste, when in fact a motor won't run without it. And we'll explain that in more detail in a minute. So I just think I've tried to find a better way to explain it, and I think I've come up with something that is reasonably good, but you'll be the judges of that. So I want to go back to some basic electrical theory to help explain it. So this is, everybody's heard of the sine wave, I think. This is in a 50th of a second with alternating current. The voltage goes in phase with the current from positive to negative, and they align perfectly. And this is what happens if you have a simple resistive load. So that's something like an electric kettle or a toaster, where it really is a simple load. There's a question that comes from this that people have said, well, if that's the way it works and you're going from positive to negative all the time, 50 times a second, and you know, how fast is that? They kind of say, well, how can anything work? Because, you know, it's basically going from positive to negative, so the average is nothing. So how can anything be powered by that? And the reason for that is actually simple mathematics. This is where mathematical theory can be shown to actually be real. And if you can remember back to your days of doing a bit of maths, you might recall that when you multiply two positives, you obviously get a positive, but also when you multiply two negatives, you get a positive. So while the voltage and current are going through this positive negative cycle, power is always positive. So you can also see that if that's happening 50 times a second, two cycles 50 times a second, if you like, or it's one cycle, but two positives, by the time you look at that over period, then that power is almost a straight line when you think how fast this is. And three-phase is even better because these curves are displaced by a third 120 degrees. So three-phase power gives you even more stable, a more stable power supply. However, we're dealing with inductive motor loads, which are quite different, and they mess around with the power supply quite a lot. And the reason for that is that when you switch on a inductive motor, the first thing it needs to do is establish the magnetic field. And it does that through the rotor in the middle of the motor. So it creates a magnetic field which sits inside the fixed magnets in the stator, the barrel of the motor. So they repel each other and the motor starts to spin. So that's basically how an inductive motor works. The problem with that is that process puts the voltage and current waveforms out of phase. So where they were just matching nicely with a simple resistive load, suddenly you've got displacement. And so the problem with that is, and this is what causes reactive power is that during that cycle, you can see that there are periods when the current is positive and the voltage is negative, or vice versa over here. And so just going straight back to that mathematical analysis, we know that when you multiply a positive and a negative, you get a negative. So what actually happens is you've got positive power. That's the real power that's actually pumping water, if you like. And you've got negative power that's called reactive power. And basically that reactive power is the energy that's creating the magnetic field within the motor. So that's happening 50 times a second again. But what it means is that from Ergon's point of view, basically you don't consume that reactive power. It's stored as magnetic energy and then returned to electrical energy. And so you just borrow it for the duration and then give it back to Ergon when you finish with it. So because of net metering, it means that Ergon have had to allow for that whole power range, we call the apparent power. So all the generation, all the distribution, all the transmission lines, all the transformers on your property have to be able to handle that much power. But Ergon, we're only getting paid for the top bit that you actually consume. So they caught up with that, and over the years they've started to charge people more and more. They're charging people for what we call KVA, because reactive power is KVA. And so that's where KVA charges have come in to compensate Ergon for having to allow for this to be provided. So I hope that makes a bit of sense.
Alan, just a quick question there to clarify then. So when you're billed as a large customer for demand in kilowatts, KW,
Yep.
you're billed for the real power. And when you're billed in KVA,
Yep,
in your demand charge, you're billed for apparent power.
yep, that's
Yep.
correct. Yeah. And
Thank
so everybody's gradually being converted over to KVA billing.
Yep.
But if you looked at T44, which is what this place is on, Andrew, you'd see that excess demand with kilowatts is anything over 30 kilowatts.
Yep.
Whereas excess demand for KVA is anything over 35 KVA. So
Yep.
they've got it covered reasonably, but you know, they're emphasizing KVA because they would actually like people to do stuff about it, try and get rid of it. And that's where we move to with this now.
Thank you.
So power factor correction basically uses capacitors to bring these back into alignment. I want to make the point that this only happens where you put the power factor correction. At the motor, it's still generating reactive power to make the motor run. So what we're trying to achieve with power factor correction on the site is basically to bring that supply, the supply of reactive power inside to your property rather than coming through the Ergon transformer. So Ergon would love you for this, but all you're doing basically is instead of that going backwards and forwards to the grid all the time through the transformer, it's going backwards and forwards to your own set of capacitors, which may be at the MSB or they can be even down at the machines. We'll talk about that also. So all you're doing is you're moving the problem, if you like. Although to me, it's not a problem. It's just real life. As I said, the motor won't run without it. So you're just helping Ergon out, and you're putting some equipment in that reduces your bill because you basically get rid of the KVA charge, and you can do that pretty much completely. This is this is called a power triangle, and it's just another way of showing what was showing with the sine waves and the power curves. So basically, this is putting a power factor correction unit at the MSB at the Daintree Saltwater Barramundi Farm. And we know from the numbers that we've looked at already that they're generally their real power consumption is 130 kilowatts. But they have, when you do the numbers, we know their power factor. This is just Pythagoras theorem. We know that their reactive power is 83. It's called kVAR, kVA reactive. So from Ergon's point of view, it looks to them like the site needs 154 kVA. So what we're planning here is to, you can see here the kVA before power factor correction, 154 versus 130 kilowatts. So the power factor itself is 0.84. So we can, by putting those capacitors in at the main switchboard, supply that kVA within the business and basically reduce the kVA to the kilowatts. So you have a power factor of 1 as far as Ergon's concerned, or very close to it, 0.997. And what that does in terms of a project is the cost of the project, as I said, trying to be reasonably conservative, 16,500. The demand saving for that reduction that we've achieved, taking it from 154 kVA to be the same as the 130 kilowatts, is a saving of 7,200 a year, which is a 2.3-year payback and close to a 44% return on investment. So great project. I think most people would think that's a pretty good thing to be looking at. So we're good with power factor correction. It's moving on. So variable frequency drives or variable speed drives provide, basically it's a process of controlling the motor speed by changing the frequency. It has a number of benefits. It completely eliminates the startup surges, and it will, if you use it to slow the motor down, and we'll look at this, it can achieve significant reductions in energy use. The other thing, what we often end up doing these days is using a variable speed drive as a really fancy soft starter and just a way to slow a pump down. The reality is they were invented originally to provide process control. So, you know, putting it in the context of a barra farm, for instance, you can, if you've got this kind of saltwater intake, you could put a level sensor at the intake, which is basically measuring the tide height, and you could use that to feed back to the variable speed drive, which will change the motor speed to maintain the operating conditions you want for, you know, this is about the famous pump curve. But you can maintain the speed just by basically make it constant through that process. But as I said, very often these days we're just using a VFD or a VSD as a very fancy soft starter and a way to, you know, a lot of people just whack in a VSD and reduce the frequency to 90% and walk away with the gains. One of the reasons I say that here is if you look at just the second point in there, reducing the pumping power just by a small amount seems to have not very much effect on the volume of flow. That's just something that people have observed. So the first principle, we've seen this chart before, is basically to bring that motor down towards its optimum operating voltage. So you change the frequency, you'll change the voltage, you bring it down on that curve. So there's a real benefit. The second is just another law of motors, if you like, where the power required or the power operating a motor varies with the cube of the pump speed. So it's not a linear relationship. So you can see that the best way is just to look at the chart, and you can see that if the speed is running at 100%, funnily enough, it uses 100% of the nominal power. If you reduce it to 90%, and this is, as I said, what a lot of people do, suddenly you've saved 20% of the energy required to run that pump. Now, you will get a change in volume. You know, and this is where you have to understand what you're doing with these things. A great place to sit, if you like, is 80%, where you're basically saving about 50%. You're running at 80% of the speed, but only 50% of the energy use. Now, got to be clear, VSDs have a dark side, and that they can create some fairly difficult harmonics. And if you try and run the pump too low, you could well start causing cavitation and all those things. So if you go down the track with VFDs, the farmer needs to find somebody that knows what they're doing to size it in the first place and to set it up. And then it can be a trial and error exercise. You know, we talked about using VFDs on the paddle wheels. Now you can use one VFD with two motors if the motors are the same size and the cables are reasonably much the same kind of length. And if it's a small motor, you don't need to worry about some of the things too much, like shielded cable and sine wave filters and all those things that add a bit of cost. So, you know, we said they have 28 paddle wheels at the farm. If you just did one pond, you could set it up, experiment with it. And, you know, this means it's not massive cost to start with. And basically what you're going to do is set it at 90% and see whether that maintains the oxygen levels you need in the water, because they measure oxygen levels all the time, regularly. Or can you run it at 80% and will that give you the volume you need? You know, there are more sophisticated ways to do that. You know, we've worked with a company called OxyGuard, where, you know, they use automatic oxygen probes to vary the speed of the motors. But, you know, that's getting into some fairly big numbers for cost. This is a way to achieve something that could be very good, much more cost effectively. So if we look, for instance, just at one of the 22 kilowatt sea pumps, install a VFD and run it at 90%. As I said, you eliminate the starting surge. It's going to run at a lower kVA. So there's both reduction in the starting surge, but also in the ongoing kVA required to run the pump. And these are the numbers. So, you know, there's that power triangle again, showing that because of the way a VFD operates, it actually has some capacitance in it. So it operates like a mini PFC to some extent, because it's basically inverts the AC to DC, and then it messes around with the profile, and then it converts it back to AC. So because it has capacitors in there, it actually helps to reduce that, or you can achieve those peak demand savings. And this is the calculator. There's lots of different calculators online to put in how you want to run a pump. And I've shown it here. You can see it's running 100% at 90% of maximum speed. Put in the motor size, the pump efficiency, the voltages on the site, and it'll tell you, you know, with the cost, obviously with the cost of the VFD, what the savings will be and what the payback will be. So if we just have a look at how that all transpires, so there's the two components of the savings. We're saying that based on the pumps running 10 hours, that pump running 10 hours a day, running at 90%, it'll save 17 megawatt hours of energy a year. At the 19-cent price is $3,000 odd, and a whole 7 kVA per month of excess demand is another $2,000. So again, you know, $11,000 install cost with a 2-year payback. It's a pretty good kind of proposition. This installation cost is for a Danfoss drive, which is a good high quality drive. And it also, because these are big pumps, they need a harmonic filter, and they definitely need screen cables. So Tsunami seem pretty professional organization, and if you go down this track, they will talk to you about making sure it works. They'll give you the pump curves for their motors with VFDs to make sure that you're trying to get in on the right spot. So as I said, VFDs are great, but you need to find a contractor that knows what they're doing, and the manufacturers will certainly help you with all of this. And then the other thing that I spoke to Mark Hober about at the time, you know, we are a Lorentz pumping agent, and Lorentz have some just outstanding equipment these days and new innovations. So rather than a standard VFD for this, you could actually install what's called a Lorentz PSK2 hybrid blending unit, which means that when the time is right, you could add solar to the system. And then the way this operates is you set the pump operating conditions you want for flow and so on. And if there's not enough solar to achieve that, the hybrid blending pump controller sucks in whatever it needs to supplement that from the grid. So this is kind of another a step beyond. And you know, I just know as soon as I saw the area of those Tsunami pumps, the inlet pumps, you can see this quite large area beside them, which to me just shouts ground mount solar system, which we love. So it's kind of something that you can come back to when the time is right. But it might be an idea, if you think you might ever do it, is to put the Lorentz equipment in at the start. Okay. And finally, the last thing that we really looked at, solar and battery system. There is no solar on the site at the moment. You know, when we look at any kind of business, the first thing we look to see is what is their annual energy use. And if it's around about 200 megawatt hours a year, we get very excited because there's a real prospect that we can get rid of 100 megawatt hours of that and turn them into a small business. So they can go back onto a small business tariff with Ergon and pay $1 a day for their service connection. Pay a bit more for the energy, but that's not an issue. And pay nothing for excess demand. And we've been able to do that just recently with a Silly Solly store, for instance. It's just great to see that. But these guys use, you know, 0.5 gigawatt hour a year. So that's not going to happen. We can't achieve that. So the first thing you'd say is, you know, batteries are nowhere near at the kind of cost where you could use them to support nighttime loads. But batteries are, you can use them in a demand response mode, which for peak shaving. So, you know, we're looking at doing this at a workers' camp just down the road from us, where we can shave the top off their peaks in the evening and get them quite a good saving for quite a small battery. So that actually is going to give them a very good payback. But the bottom line is that a 100 kilowatt solar system, and most people know why 100 is a good size, because you still get the government subsidy for the panels, which is worth a lot of money, is going to give them a pretty reasonable result. So just looking straight, this is kind of bread and butter stuff to us, but a 100 kilowatt solar system on their processing shed, which will fit fine, will generate about 164 megawatt hours in that area and that latitude. This is quite a conservative cost again, but shows a 4.8 year payback, a 21% return on investment. So once you've got your 100 kilowatt solar system on, you can always look at it again then later and add more. And then at that point, you don't get the government STC subsidy, but you get the LGC subsidy. But you always do the first 100 first in order to get that benefit. It's worth too much. And that's it for the projects. I just wanted to mention pump setup and pump efficiency. It's not that we're ignoring it. It's just that in our experience, pretty much everywhere we go to has not got pressure gauges on their pump systems. They certainly don't have flow meters. They don't have lengths of pipe that are accessible, that are clean lengths of pipe where you can strap on a ultrasonic flow meter. So I'm not saying those things shouldn't be done, but I think we can do all these other things first and get great results, and then as they get more time, they can try and get these pump stations set up with the right kind of monitoring gear so that you can then come back and look at the pump curves properly and make sure that you're in the right space. This is a summary of the projects. This time they're in order of payback, if you like. So obviously the alternative retail and the retapping the transformer is at zero cost, just time. And then we did the exercise for VSDs on pairs of pond aerators, paddle wheels, and that's the fastest payback. We'll just assume we can run them at 90%. As I said, this is something that has to be proven before you jump in with all, completely. And then the next benefit was the river pumps. They're not river pumps, but you understand they're the inlet pumps from the seawater. And then the same really applies. The bigger sediment pumps, 7.5 kilowatt, is the next cab off the rank. Then PFC, the smaller 5.5 kilowatt sediment pumps. We've made assumptions after talking to Mark about how long these run a day and those kind of things. That obviously has a big impact on the saving. And then the final one is the solar system. So, if you say that we started looking at their bill at 170,000, to take $100,000 off that would be a pretty good result. But it requires $258,000 of investment, and they're not in a position to do that at the moment. But there's nothing to stop them doing, as I said, starting to do some work with VFDs on pond aerators and things like that. And again, I just got to keep saying, you just don't do all of these because everything you do in there, well, apart from alternative retailer, is going to impact the baseline and potentially change the sizes and the specs of the other equipment, whether you work from the VFDs back to voltage optimization and PFC, or whether you work from both ends to the middle, or whatever you do will have an effect and change the requirements or the spec of the equipment you would want to use. And I'll just, we had some great assistance with this. Mark himself spent a lot of time with us, and he's a class act actually as a farm manager. I had a lot of help from Captech Australia, who we know reasonably well. They're part of AMP Control. If you know the name, that's a massive business in Australia. And Garth from Tsunami Australia and Glenn Miller from Reaqua gave me lots of good advice. So I'm exhausted. That's it.
Excellent. Thank you. Thank you, Alan. I'm not surprised you're exhausted. You covered a lot of ground for us.
Yeah, well,
and like
get up
we said,
early.
Alan and I were just talking before the webinar and talking about his electrical perspective on the audit, which is very clear from that, but very interesting in the way that you've explained the voltage, the power factor, and the function of variable speed or variable frequency drives is excellent, and I think will be very useful to a lot of people watching this webinar. So I really appreciate it.
I did put the copyright thing on that stuff, did I, Andrew?
That is good, and I
hey, I'm old enough, I don't mind anymore, whatever. If anybody can make use of it, they're welcome. Yeah.
It was good of you to explain the function and how it, particularly with power factor, and critique the beer analogy, because yeah, the way that you've illustrated that is excellent. So thank you very much for your time and your expertise in doing that, and for the good work that you've done on those
No problem.
audits that you've done for us. Yeah,
It's a privilege to go and work with these guys. I just think they great people, you know. And as I said, Mark in particular just had an awful start to the year, as you can imagine. The only way he could get around his farm was in a boat.
Yeah.
Dodging crocodiles. So
Yeah.
no,
It's not good. Yeah, unfortunately, a lot of farms have been affected by natural disasters in the last couple of years too. So it's it's quite it was quite moving to hear Mark's story when we first.
he was still a little traumatized, to be honest, but
yeah, not surprised.
Anyway, he's tough. He has to be.
And thanks again for the webinar. I'll just run through a couple of things to wrap up. But as I mentioned at the start, we've set up the Queensland Ag Energy Hub at QFF with the website details below there, and it's you can access it by just using that QR code on the top right corner. But we've designed that to put all of our energy resources that we've developed over the years at QFF in one place. So there's over 120 odd case studies, there's fact sheets, there's top efficiency tips by sector, and there's lots of other different information about what programs are available and what funding and grant schemes are available at the time. So we try and keep that up to date. And importantly, if you're a farmer and looking for energy efficiency information, you can search the case studies by sector, technology, irrigation, location to find ones that are relevant for you. So please jump on and use that resource. If you're in the south part of the state, in one of those 6 local authority areas there of Southern Downs, Gundawindi, Western Downs, Toowoomba, Lockyer Valley, Scenic Rim, we at the QFF Energy team can come out and do a Type 1 energy assessment with you at no cost. So that's a Type 1 energy assessment plus a walkthrough, and we'll talk to you about on-farm emissions and those kind of things as well. We are looking for farms that are keen to participate in that, so please get in touch with the team, and I'll show some contact details in a minute too. We also have an energy information service for landholders. We're trying to, on the back of all the energy efficiency and renewable energy work we've done, and the preparation of the renewable energy toolkit, in conjunction with the Queensland Government, we're able to provide this advice line so landowners can call and talk to us about energy tariffs, energy efficiency, renewable energy, or if there are any questions that they have over the energy transition. So whether you're impacted by proposed energy developments, transmission projects, or nearby energy renewable energy projects, please give us a call if you've got any questions, and we'll help you. And if we can't, we'll point you in the right direction for some good help. The number's there at the bottom, and there's also a telephone number and email address there, and a link through to the main QFF website. So please get in touch if there's anything that we can do to help on behalf of the QFF team. So on behalf of the rest of the team, Jonathan, Sam, Steph, and our presenter, Alan, I'd like to thank you very much for joining us today and listening to the webinar, and we'll look forward to being in touch soon. Thanks again, Alan.
Thanks, Andrew. Thanks, everybody.
Thanks, Jonathan. Thank you.
See you next time. Something like that.
Yeah, see you next time. Great. Thanks very much. Bye-bye.
Okay, bye. Bye.
Just stop.